from our wonderful vendors. I would like to throw some of this stuff, but I'm going to throw it into the audience. So if you would like swag, move forwards. So, as always, we have a lot of stuff going on. There's a lot of really good training going on. If you haven't head over to the Lockpick Village, I highly suggest it. There's some amazing art being created for Hackers for Charity. And they're doing that art live on the fly. Some beautiful prints are also available for sale, and all of that goes directly to Hackers for Charity. So you, sir, want some stuff. So here, have a flashlight. Trust me, it does work. You have to take the little thing off the battery. Well, somebody else that listens, but can't catch. Yeah, you're supposed to stay in the front. So this is a really big room. If you have questions, there is a heckler mic right in the middle, or come all the way up to the front. These guys will be great for to answer whatever questions you have. Note, you all got a ball. We are ShmooCon, the only conference with balls. Those balls are not stress balls, such that you can relieve your stress. If you're seeing a presenter, not like you guys are, but there are other presenters that are going on. If you see a presenter that you don't disagree with, the reason you have those balls is so you can take them and chuck them at the presenter. It's sometimes it's hard to stand up and call out somebody and say, I don't believe you. I think what you just said is bullshit. That's why we give you a ball, so you can stand up and chuck that and you visually display the fact that you don't agree. So, I'm sorry, but if you receive balls, and you can throw them back. So, awesome. So, the last thing that I have before I throw my last t-shirt, feedback@shmoocon.org. If you have any feedback, whether you really love a presenter, whether you think that we are doing something really great, if you think we're doing something we need to change, please let us know. We take all of that feedback to heart, and we try and respond to each and every email that we get and communicate with each of you, because we want to make this the best conference that we can. So please send emails to feedback@shmoocon.org, and we will read and respond to every single one of them, as long as they're not automated spam. And we want to make this con as best as possible. So with that, I will toss my last shirt to somebody else that listened, and then introduce Sarah and Jon, who will be talking to us about software-defined networks.
Hooray.
Are we on? Okay.
Good morning. Can everybody hear okay? Glad you all made it out after the crazy evening of frivolity last night in here. It looks like they cleaned it up pretty well. First off, just a disclaimer. I just noticed the screens are actually in front of us. We are going to be needing the laser pointer for the demonstration portion of it, and so the cameras are back there. If you do not want to be in a camera, I'm going to be probably standing right about here so that I can laser point to the screen. So if you do not want your picture taken, probably steer clear of these few seats right here, because you may end up being in the background of something. I know how they deal with cameras here. Welcome. It's really good to be here. Today we're going to be talking about something very near and dear to our hearts, and that is software-defined networking. Just a little introduction on who we are. We are both very, very passionate nerds that focus on the network side of things. We love everything to do with networking. She handles a lot more of the building, and I handle a lot more of the securing. Securing. And so that brings up a really good point. So a lot of people here, nerves, this and that, have fears about speaking up here. The shmoo balls, people in the audience that are definitely way smarter than me. Actually, my greatest fear here is getting in a fight with her on stage, because while we research together very well, we do it amidst violent disagreements. So that's what I'm scared about. Second quick note about the shmoo balls. We are both very aware our weakness is speaking very quickly. So we will expand the use of shmoo balls to encompass, if we are talking too fast, feel free to let us know, because we both do that a lot, especially me. Software-defined networking. So just before we start here, how many of you have heard of software-defined networking before? Sweet, a lot of people. How many of you have actively worked with it, securing, building. Okay, look around real quick. Please keep your hands up. Look around. There's a few that shot right up, a few tentatives. Software-defined networking is huge, and she's going to go into in a second some of the companies that are using it. Why is there so little representation here for something that is increasing, as you can see, in billions of dollars every year? Market research is anticipating $12 billion by 2019 on the conservative side. You can see things way greater than that. I usually go on the conservative side, and that's what they're saying by 2019. So what is the reason behind this? Why? Who's using it, first of all, and why aren't we hearing more about it? Why are only a few hands up when we talk about security within software-defined networking?
Well, the answer to that is software-defined networking is actually kind of complicated. It's not like setting up a traditional network, which I love doing. It actually requires a little bit more. You need architects, you need coders, you need security people, you need network folks like us, because software-defined networking has a lot more pieces. As you can see on the screen, there are lots of large corporations, to include NSA, that are using SDN, and they have been for years and years. Google actually developed their own controller, Andromeda. So all of these companies are using software-defined networking because it's a very powerful tool and it's able to meet the needs of their large data centers that traditional networking is just failing.
The issue we're trying to bring to light here is that those large data centers have been using it a while, and it is expanding in getting lower and lower in the stack, as we're going to show here, and how the amazing capability that it has even for smaller businesses, smaller companies. A few of the solutions that are out there right now, they're commercial, open source. It really started as almost an open source, community-driven project with a lot of commercial vendor support, a lot of vendor buy-in. So companies like HP, Brocade, Dell have lent engineers to the SDN project to essentially help develop this capability. So you can actually buy hardware switches that have SDN built into it, SDN capabilities, OpenFlow capabilities. We have a network stack here that we're going to be using a little bit later to show you guys a few things, answer some questions. But if you don't have a lot of money to pay Brocade or pay Dell or HP to come into your workplace and set it up for you, you're going to need to do some research and studying on your own. And a lot of that can be done through a lot of the open source platforms. A lot of the controllers are built on the Open Daylight and Floodlight platforms. Those are the two most common controllers that are out there. There's a few others up there that we listed that are great for different purposes. Open vSwitch is a virtual switch that handles OpenFlow, so you can actually completely have an entire virtual SDN inside a single VM for your own research or study purposes. It's a great tool. And then VMware and Cisco have kind of baked their own flavor of it, as especially Cisco likes to do. So VMware does it because of their integration with virtual machines. Some of the stuff there, they need some specific functionality, and Cisco was not happy with some of the stuff that OpenFlow protocol had, so they rewrote the protocol a bit to fit their needs. So what actually is SDN? We've been talking about it a lot. What is it?
Well, I know a lot of hands went up, but we're just going to review a couple things. What is SDN? Really, SDN is abstracting the function of the control plane and the data plane from a network device. It's moving those into separate locations logically, okay? I do want to make the distinction that SDN is not the same as network function virtualization. There's a lot of confusion around. When you're doing network function virtualization, you're taking a networking device, a switch or a router or something, and you're abstracting the functions that provides for your network from the hardware, and you're virtualizing that. Now, they are very complementary to each other. NFV can be used to virtualize your data forwarding plane devices, your switches that are going to be operating in your SDN environment. But let's get a little bit deeper into the weeds with SDN. So if you look right here, we're going to center on this picture on the controller. The controller in an SDN is your logical point of control. It handles all your control plane functions, right? Where do I send traffic? What do I do with this traffic? What's going on? The controller itself is generally run as an application on a Linux-based platform. And then we have some control channel lines here. The control channel lines are connecting the controller to the data forwarding devices. So like I said, the control plane functions were abstracted and we moved those to the controller. We've taken the data forwarding devices down at the bottom, those OpenFlow switches, and they're handling all of my data plane functions. So the controller needs to be able to communicate to these devices. They use the control channel, and we'll go a little bit more into the control channel later. But that's how they're going to be communicating instructions, basically. And then at the very bottom, we have all of our hosts. Our hosts are communicating with our data forwarding devices through the OpenFlow protocol. This is what we call the southbound plane, and we're going to be doing a lot of talking on the southbound plane and the control channels specifically. The northbound plane, which is where the APIs reside, basically communicates to the controller and augments the ability to produce flows, to have special functions. There's a lot of security and a lot of flow-based functions that are coming from specialized plugins and APIs that are either vendor developed or open source developed, not so much. But that's what's happening at the northbound plane. So that's your SDN environment in a nutshell, but what is it really? So basically, this is a really, really layman way of explaining it, but my controller is going to be sending my flows to my switches. I put on here think ACL because my flow is a little bit more than what you would understand in a routing table or a switching table. So your controller is going to send this flow information because it has the control functions down to my data forwarding devices, the switches. They're going to use these flows in their flow tables. When they're receiving information, they're going to look for a match in their flows, and then they're going to just do whatever the action is, forward that out, drop that traffic, whatever is appropriate. Now, if the switch receives something from a host and it doesn't have a flow that matches, it goes through all the flows and nothing matches. Now, what the switch is going to do is it's going to take a packet from that transmission and it's going to punt that up to the controller. The controller is going to be able to either send instructions to the switch on what to do with that type of traffic, or it may need to further send that information up to one of those APIs or plugins to let that process and provide instructions. So either I got a flow from the controller, or probably I'm going to end up dropping that traffic. Now, it's not necessarily a drop action. We'll talk about that a little bit later. You may have a flood rule that you didn't take out of your switch, which you should do, and that will cause that traffic to flood out all ports, but we'll hit that a bit later. So at this point, you're thinking, okay, now I'm stopping a traffic flow and I'm sending something to the controller, which is going to process it in software. That seems kind of slow. This doesn't sound like a good idea for a large data center for this type of application. Isn't software slow? Why would I do this? Well, I would do this because of the control that I have. Ultimately, that first packet that goes to the controller in a packet in message, that is going to take a few milliseconds more, okay? But after that, all the subsequent packets in the traffic, as long as there was a flow provided, are going to be processed at line speed, okay? The controller itself can handle, the controller and the switches themselves can handle logic, matching logic from layer 1 all the way through layer 4, and any combination that you can imagine just about of all of those different layers. The APIs themselves are able to handle some functions of looking into the payload for deep packet inspection, but that's not something that is currently supported in the OpenFlow side where the controller and the switches reside yet. However, those APIs do provide us the ability to really look at traffic dynamically through every layer of the OSI and make decisions, okay? So that's a huge, powerful tool. And by the way, this is all programmatic. This does not require human intervention the same way a traditional network does. Yes, I'm still talking. So we've been talking about flows. So I wanted to point out kind of two basic ways that you can imagine how I can create my flows in a network. Again, flows are what we're using in order to forward our traffic. So we have a proactive type of flow and we have a reactive type of flow. The proactive flows, think about those as an architect or an engineer. You're going to decide the paths through your network that you want your traffic to travel. This means that your controller needs to have an accurate idea of the topology, and we'll get into that later. And this type of formulating your flows and your paths is more static, but for that reason, it's a little bit more secure. I'm not going to have any surprises, okay? But when we start saying static and secure, I feel like we're losing some of the benefits of the flexibility that SDN provides us. So that's when we can look at reactive flows. Reactive flows are enabled by the controller. And these are going to be based on those packet ins. Like I said, when the switch gets something from a host and it doesn't have a flow that matches, it sends it to the controller. The controller can either itself or through the APIs provide instructions in a reactive fashion to that particular packet. So this can be resource intensive if I have a lot of traffic on my network that I haven't planned for, and all of those packets are getting sent up to the controller. So it doesn't really scale well. So the answer really is have a good mix of both proactive and reactive flows. So before I get to my last slide and then I'll stop talking, we're going to talk a little bit about the anatomy of a flow, just for you guys that may not have, you may not have dug in that deep into what flows do. So this is kind of what a flow looks like. You're going to have a flow table in your switch or many flow tables in your switch, depending on the hardware that you're running. The rule portion, that's very important. That's going to be your matching field. So like I said on the bottom, you can see there that the switches in the controller are able to match based on any fields, layers 1 through 4. And please understand that there are things that are not depicted here that we do see special applications that can match for, like DSCP codes for QoS and things like that, actual fields within the IP header. So that's really amazing. So there we have the rule. The next part is, once I've matched something, I've said, okay, this traffic matches this particular flow. Well, what do I do with the traffic? That's going to be my action. Understand that action and instructions are synonymous. I'm going to use those terms, both of those terms, because the term actually changed from action to instructions as they added capabilities with the newer implementations of the OpenFlow protocol. So my actions, right here we just have some very generic actions that can be taken. I can forward the packet either to a port or ports. I can forward the packet to a particular destination based on an IP. I have a lot of options here. I can also send that packet up to the controller. That allows the controller to process it or send it to an API for further instruction. I can drop the packet, obviously. And then the normal forwarding pipeline, that's something we will hit again later. That means that basically I can treat this particular traffic the same way I would in a layer 2 learning switch, okay? Don't worry about stats. We're not worried about that. So, SDN. Really what this is security and networking. Did we just become best friends?
Yup.
Yep, security, networking. So, the beauty of SDN, in our opinion, is that you can marry these two things, okay? So, I talked a lot about flows and how you can use flows. Before we get into the security portion, because I know you guys are all waiting for him to talk about security, I want to point out some best practice ideas for creating your network in a secure way. Okay, so now instead of just routing to get there, I can route to get there the way I want to get there in a secure way. So coarse and fine-grained flows. I have the ability with all these matching options to match something very coarsely, right, like all IPv4 traffic. It's pretty broad. Or I can have very fine-grained flows that specify specific host in a specific VLAN with a specific destination in mind. There's all sorts of things we can do there. So in a large SDN environment, think about your core switches and routers. You want those processing large amounts of data very quickly. So those are where my large, coarse, generic type flows are going to be placed. And then around the edges of my network, that's where I'm probably going to have my finer grain, granular type flows. And some of these may be a product of those reactive flows that we talked about. Also, something that we didn't really see when we talked about the anatomy of the flow is the priority. I mentioned that you have flow tables within your switches. The priority is something that you're going to assign to the flow. And think about it like if I have a higher priority and it matches, that's the flow that's going to be used before this lower priority flow, even if it also matches that. So think about how that kind of, again, gives me the ability to treat these flows almost like an access list in a firewall. I can also use multiple tables within my switches. These tables allow me to really separate my traffic, and I can set an action for a specific match to just refer to another table. So let's just say generic, just simple example. I have IPv4 and IPv6. I'm running dual stack in my network. I want all my IPv4 to do these things, and I have this whole table created full of flows. I also have a very broad match for all IPv6 traffic based on ether type that the action can be send it to this flow table, because I don't need it to process through all these IPv4 flow rules, okay? So, I'm about done. SDN is really awesome because when your network's under attack, we feel that flows can retaliate, and we're going to talk about that.
Security. Finally, security. There are really three main avenues of attack of an OpenFlow, of an SDN network. These are very broad avenues and generally collect most of the various types of attacks you can see on an SDN. One is the control channel, that communication link between the controller and the switches. The controller itself is also another avenue of attack, as well as the flows within the switches and the flows that are being sent to the switches. We're going to look at each one of these things and give you a few aspects of each one that you need to be aware of. For the control channel, once again, this is the communication between the controller and the switch. And so it's very important that it is secure. The control channel itself can be managed in-band or out-of-band, meaning out-of-band, it's running a completely separate TCP network outside of the OpenFlow network. And that is great because it's actually physically separated from your OpenFlow network, and there's a lot of security associated with that. However, manageability can suffer a little bit because now you have to have places that can route to that separate network. In-band makes management really great because from within OpenFlow, you can now manage your controller from any OpenFlow host, really. Obviously, you don't want every OpenFlow host managing your controller, so there are security associations with that as well, or security implications associated with that as well. That control channel can be secured with TLS or TCP. Initially, the OpenFlow protocol specified that it was required that that control channel be secured with TLS. Well, you start requiring things like TLS and people start complaining. And so later editions of the protocol now allow for both. And guess which one most people are using? Not TLS. So there is some overhead associated with TLS and implementation. Yes, you have to actually load all your certificates on the switches, which can cause problems. So a lot of people are using TCP still to manage their control channel. We'll talk a little bit more about that later. The control channel is just a TCP network, so it's vulnerable to all the traditional network attacks that you will see on any other network. Here's a listing of a few of the attacks we were actually able to successfully leverage against that control channel. I mean, you all remember EtherCap. I used it in high school to move traffic around my library, but you can still use basic tools like that, layer 2, man-in-the-middle attack on a controller versus a switch, and now you can see every bit of traffic that passes between the controller and the switch and inject traffic as you see fit. And we'll talk about that a little bit later as well. This allows you to impersonate the controller and make switches think you're the controller, potentially taking over the entire SDN. So it's very important that your control channel is properly secured, because in addition to that, the denial of service behavior the switches have can depend on how you program them. So if a switch loses connection to the controller, it essentially goes into one of two states. And most familiar, you could probably use the fail open or fail closed ideology. So fail secure is the more fail closed. Basically, the switch behavior, if it loses connection with the controller, is to just continue processing traffic based on the flows it has, and when those flows time out, the switch just drops traffic. That's the more fail closed mindset. The fail standalone means the switches process the traffic as if it was a normal switch. So basically, you reverted to regular layer 2 switch, and the switch will process traffic that way. Clearly, both have security issues and availability issues, and you need to make a careful choice which one you choose to implement. Right now, I'd like to do a quick tip of the hat to Mr. Gregory Pickett at Hellfire Security. He's one of the few other people that has talked at security conventions about software-defined networking. If you look for HackerCon security convention talks on SDN, it's really him. Maybe a couple of folks at RSA. There's not a whole lot of discussion about this. And so that's what we got excited about it, because we love networking, and there's so much potential for security within software-defined networking. We felt that it really needed to come out to a wide audience, and such as the ShmooCon group. Mr. Pickett developed some great Python-based tools for OpenFlow version 1 that can enumerate OpenFlow networks, can DOS controllers, can impersonate switches, all kinds of great tools. Those can be found on his website at Hellfire Security. Recon. Obviously the first stage of any successful attack. What can we learn about an OpenFlow network from within an OpenFlow network? Well, oddly enough, depending on the way the switches are programmed, your OpenFlow ports can be scarily quiet. So you plug into an OpenFlow port and turn on Wireshark, and you may actually not hear anything. Your broadcasts are managed at the switch, between the switch and the controller. So your typical ARP broadcasts, your MDNS, all that other stuff that Microsoft does is not actually getting broadcast, because the controller can specify exactly what to do with all that stuff. And so you may actually, depending on the configuration, not actually hear anything plugging into a port. So there's a great security implication there for you're not able to just passively sniff a lot of information about an OpenFlow network if it's properly configured. Occasionally, though, you will see LLDP and host identification messages. Those are a way the controller manages the links and looks at tracks where the hosts are on the network. So OpenFlow uses some LLDP variants to track hosts and link states within a network. Another interesting thing we noticed was we could start fingerprinting the flows based on hits and misses. Once we were able to listen on the control channel, we could start sending traffic in OpenFlow ports and see what the switch was sending to the controller and asking about. This allowed us to fingerprint exactly what flows were in the switches based on, hey, the switch sent this traffic someplace, didn't send it to the controller. The switch clearly had a flow for that piece of traffic. So we can now begin to enumerate the flows within the switches. In addition to that, some of the default flows, when you open the box, plug in a controller, plug in the switches, it'll install a lot of default flows to just make your network work. And some of those include, as she mentioned, the flood flows. You send a packet in. If the switch doesn't know what it does, it floods it out all ports. Essentially, either switching or hub type mentality, depending on the controller you're using. This can allow you to plug one thing into two OpenFlow ports and listen on one and send random traffic up this one and see what's getting flooded over here. So you now know what matches within the switch. Lastly, you can actually conduct a hello sweep of the network and pinpoint OpenFlow capable devices within the network, because the default behavior for OpenFlow devices is to respond to hellos. So you send a TCP-based hello and see who hellos back. This can allow you to pinpoint the controllers and, depending on the implementation, some of the other devices as well. So a lot of times when you start talking TLS and security specifically with software-defined networking folks, they will hand wave it by saying just TLS, use TLS. TLS is a great tool. I don't know, there was a great TLS talk yesterday. I don't know who all went to that. TLS is a great tool and can provide some great security, but it's definitely not the answer to everything. And there's some specific things we need to be mindful of when implementing TLS on an SDN. Unfortunately, it's not as easy as just implementing TLS. There are some things we need to think about. This is a hello packet. Our issue is this is the exact specification of a hello packet. We know exactly what's inside that packet. The protocol is predictable. So inside that hello packet, I know that it's 19 bytes. There's no padding. There's no random transmission IDs that are generated. It's a sequential transmission ID that's generated. So when I see an encrypted 19-byte or plus the TLS header, 19-byte packet go by, I now know exactly what that packet is. As you can see here, I have a hello packet next to its encrypted counterpart, and it's very simple and straightforward. We know what every field in that packet is. So based on their size, and that's just a hello example, there's echo requests, echo replies, there's many other packets that we can identify based on their size. So now we can man in the middle your network, because once again, there we go, layer 2 attack. You can still man in the middle a TLS connection. And we can now swat packets we don't want based on their size. So I inject a bad flow into your switch. The switch goes to update, or the controller pulls the switch, and the switch goes to update the controller. I can just knock that packet out. I don't care what's inside it. I know it's an update because I know what the size is. And I can prevent the controller from receiving updates from those switches. I can conduct recon of your network based on traffic statistics. So I can write scripts that will look for these size of packets and generate information. Okay, this end of the network, the flows are pretty coarse, and there's a lot of packet ins to the controller. I can start getting a lot of information about your network just based on the packet sizes that are coming across, even without knowing the contents. And lastly, since we know exactly what's in that packet, we can begin hashing these and creating rainbow tables that will eventually start fingerprinting your keys within your network. This is a significant problem, as this tells us a lot, and it is not secured by the encryption. So the encryption does not defeat all the things we can find out about these packets. So we've talked a little bit about the control channel and the implications there. The next avenue of attack is the controller itself, and she's going to talk a little bit about that one.
Aren't you guys glad it's me again? Just kidding. So the controller, like I mentioned before, the controller is my central point of logic, okay? The controller is going to be the brain, the heart, the soul of my SDN. So the controller really is a single point of failure, and I know a lot of you are thinking that, like, oh my God, if the controller goes down, it's over, right? Well, first off, you don't just have one controller in a large network. You have usually overlays of slices, and those controllers have different slices of the network, and you have failover mechanisms and high availability, but we're not going to go into all that. What I do want to point out in terms of the controller is that this controller is an application that's running on usually a Linux-based platform. So whatever vulnerabilities are inherent in that platform, if you haven't patched it, now your controller is vulnerable, so be careful. There's really nothing new there. Now, controller and API fuzzing. This is fun, and there's a lot of people that have done research on this. You have just a myriad of APIs and plugins that have been built to interface on the controller and provide additional functionality. So the idea is, from the data plane, if I'm sending in packets that are malformed, have unexpected payloads, just all sorts of different variables, if I'm sending those in and thus causing the switch to relay these to the controller via the packet in message, the controller may get this and freak out. It might pass it up to an API and freak out. The key here is, when we start looking at fuzzing the controller and the APIs, it only just takes one packet to crash my stack. So secure coding is very important, and I know that's not maybe you guys' problem, that's the vendors. But on the open source side, it's something that we should be cognizant of. Controller overload is also a problem. There's a lot of talk out there about denial of service, distributed denial of service. Obviously, I've talked about these packet-in messages a lot. If I have enough hosts that have been compromised, or if I have the capability to send a very high rate of packets that I know are going to get packet-ins generated because they're missing those flows, there's nothing in there that matches, that's going to get sent up to the controller. If I overwhelm the controller with a high rate of packets, a large number of packets, then I consume resources and I've basically DOSed your network. So the idea is control plane policing can help. There's a function called metering that absolutely can help. However, vendors generally just suggest you meter, okay? You really need to meter your traffic. And then lastly, in terms of the controller, topology changes are very, very near and dear to the controller because, like I said, the controller needs to have a good logical idea of the topology in your network in order to make those decisions for those reactive flows. How am I going to determine the best way to get from point A to point B if I don't know what your topology looks like? So we have LLDP variants that John mentioned before. You'll often see this particular function referred to as OFDP, open flow. The controller itself is going to, by default, be running a host tracker service as well as a link tracker service. Now, the host tracker service may be something that you look at turning off, because what it's doing is it's looking for all the individual hosts. In a large data center, you may not really need that, okay? And you may think about turning that off, because that is something where those hosts that are directly talking through the SDN network have the ability to push those LLDP variant messages in. Now, if I can control one of those hosts, if I can just exploit one of them and I can start spoofing messages, I can start sending instructions to the controller telling him that me.1 moved over there. Now I'm over there. Now I'm over there. So that's a problem. It's going to confuse the controller, and it's really going to cause issues. You can turn that service off, but again, it's something to think about because those are easy to spoof. Now, on the link tracking side of this, those particular packets, the time to live doesn't decrement normally, so it's easy to relay from a host position, relay packets, spoof packets, send things around, and make links appear where they really shouldn't be. Okay, so obviously this again is an issue because it may cause the controller to create flows where it shouldn't be creating flows because it doesn't have an accurate idea of the topology. So one suggestion that I have read about in terms of securing this particular issue is, at least for the host tracking service, to have some sort of a precondition check. Authentication for those messages, it's just too heavy and it's too much. So a precondition check would mean that if I send you an update that says, hey, I moved over there, my port better have gone down over here and up over there. And that's something that the controller is going to be aware of because those messages are going to come from the switches to notify them of status changes within their configurations, like their ports. It's enough about the controller. It's very important, though. So the flows. I just keep coming back to the flows. The flows are very important. Like John mentioned earlier, that flood flow, I kind of want to back up and talk about that for a minute. That flood flow, that is usually, when implemented out of the box, priority 0. Meaning that if we didn't match anything of a higher priority that would have been reactive or put in, that's where that comes in. So when I said think about it as if it was an ACL, that's like an implicit permit at the end of your ACL. That may not be what we want to do. We may want to think more heavily about going towards the implicit deny. So maybe have a flow in there with a higher priority than 0 that drops your traffic. So your flow types, your generic ether type flows, are going to control your LLDP, ARP, IPv4, IPv6, all those things. It's very important to be aware that, again, many controllers, all these different vendors have different ways of handling it. Many controllers are going to send very generic type flows, very, very coarse type flows to help facilitate this traffic getting to the right place, okay? The flood flows and the normal forwarding, the flood flows are going to happen those are going to happen out of the box. The controller is going to send this to the switches, and that's going to say anything that you receive on an open flow port, send that out all other ports. The normal forwarding is, hey, treat this traffic like you were a normal switch. This is something that's going to be available on your hybrid type switches that allow you to do both traditional pipeline forwarding and your open flow. So flow injection. Flow injection. That is the real danger. We talked a lot about the man-in-the-middle attack and being able to get into that control channel, impersonate a controller, do things like that, even just spoofing packets and sending them in when I see TCP. So the idea with flow injection is if I can somehow circumvent all of your security and I can man-in-the-middle your network, I can inject flows. So now that I control where your network goes, if I have bad traffic that I want to get through your network, I can redirect that traffic around your existing firewalls, your IPSs, your IDS, whatever you happen to have in that SDN environment to try to protect your information. So I'm just going to reiterate, flows, think of them as not only moving packets, but also a way to secure your network. So our philosophy. After really digging into SDN, we really felt strongly about the fact that SDN is the capability to make your network more than just packet transport. So network topology can be changed in milliseconds. That's something that we're going to go through in our demo. And this is something that's done with zero human intervention. You can have code that triggers on a condition that can change the whole topology of your network based on providing flows, deleting flows, reordering flows, and changing where your traffic goes. So something to think about once we get to our demo, moving target defense or offense. This is something that's been talked about in SDN, and there's a lot of theories, and we kind of have our own spin on moving target defense or offense, but the idea is I can very easily relocate a host. I can redirect traffic very easily. What's very interesting is in the newer implementations of OpenFlow, you're able to not only in terms of actions forward something, but I can change all those aspects that I matched on. If I matched on your source IP of .1, once I get that, right, comes in the port of the switch, I can actually change that, and you're no longer .1 to everyone else, you're .2. So it's kind of like, think NAT if you're a network person, right? That's how I think of that. But it's not. It's far more powerful because that condition, changing you to .2, can be only when you're talking over here. When you're talking over here, you're still .1, that's fine. Or maybe you're .3. So there's a lot of power in that. Just like with traffic redirection, being able to redirect my traffic based on a defensive or an offensive mechanism, very, very powerful.
So what's the answer to all this? What do we use SDN? Is it secure? Is it insecure? We need to move forward with this as a security community and help build the security within SDN. Because once again, as it happens so much, this protocol is being built and security is you know, it's behind there, but it's kind of struggling to catch up. We need to build this protocol with security in mind. TLS was a great solution. That's not the only answer, as you can see. Most of the security functions of SDN currently are plugins to the controller. That's great, and there's some great ones. I have some listed up here. For example, the HP Net Protector can actually scrub DNS traffic. So it puts a flow into all your switches that shoots DNS traffic over to a whitelist or blacklist, and you can control what DNS traffic gets to go through your network. DDoS protection. There are DDoS scrubbers built into SDN. So as soon as it detects a lot of weird stuff matching your flows, it'll start sending it to a DDoS scrubber. There's some really great plugins for the controller, but what we really need is a holistic solution that looks at the network as a whole. For one example, it is possible to inject flows into switches and the controller not know about them. So we need a solution that can pull the switches and the controller and determine that everybody's speaking the same language. Hash the flows that are in the switches, hash the flows that are in the controller, compare them against each other, and make sure that everybody's on the same page. What we can do now with SDN, is we'll demonstrate in our demo, is we can leverage existing security assets you have, your snorts, your tripwires, all these sorts of things into an SDN so that your network can actually dynamically make decisions based on alerts from those things. Obviously, most importantly, though, is do your own research and testing. There is no cookie-cutter solution for SDN in a network. Every company is going to run it differently. Every company is going to have different network requirements. That's why we go back to the it's complicated thing. There are some amazing control and beauty in SDN, but it is a little tricky, and it won't, unlike a regular switch routers, it kind of semi one-size-fits-all. SDN is not like that. So let's talk a little bit about what we've done here leading into the demo. First of all, we are here because we love this stuff. I was finishing up my master's degree. She's been in networking her whole life. We just are passionate about this stuff. We both have happy consulting jobs. This is something we've been researching on our own time because we've been wanting to get it out there to the security community, how important this stuff is. So what we're trying to do here is we're trying to create a vendor-agnostic framework. So many of those plugins that I spoke about are vendor-specific. Yes, Fortinet has a great plugin, and it only works with Fortinet equipment, which hopefully you all have patched as of like last week. Vendor-agnostic framework is really important. We need to start an open source discussion on how we can, as a community, build security within our software-defined networkings and leverage the power of it. A lot of the capabilities of security at SDN are still in a white paper or proprietary phase. So companies go off and do their own thing, build their own proprietary plugins, or college students are trying to graduate and writing white papers on it. We need a lot more grassroots support from the community to do this. The flow logic for this security model can be based on the type of attack. So if it sees a snort alert come in for a DDoS or shell code coming across your network, you can now redirect that traffic whatever you want and wherever you want. And the logic that can support that is not that complicated. You essentially just can pick what you want based on broad categories. You all know about snort categories. You can pick it based on categories of attack and granularly define flows based on that. So we're going to lead into the demo here. Let me take the clicker. I'm going to move up front here so I can laser point. Here's what we have built over here. And what we're going to do is we're going to zoom in on each one of these and give you an idea of what an SDN looks like and how we've created an appliance that can, or a proof of concept of an appliance that can redirect traffic dynamically based on attacks within the network. So what we have here is, let me do this. There we go. Grab the more powerful laser pointer. So what we have here are 3 Brocade switches, and we have them right here, and running an HP controller managing them. So each switch has a different host hanging off of it. This switch has our attacker. This switch has our honeypot. This switch has our victim. And up here we have our snort sensor and our log server, as well as this handy-dandy security appliance that we've been working on. Now, full disclosure here, we're trying to minimize the number of VMs we had running in here. So our attacker's kind of dumb, and our victim is also our snort sensor. So attacker decides to attack the snort sensor. Got it. We got a dumb attacker here. That's basically what we built. And so if you'll, I've got the clicker. Let's look first at what the controller looks like. Status quo, normal flows in the controller. So what we have here is the HP SDN controller. It has a lot of great functionality and a great user interface that works really well. And so after this, if you'd like to take a look at it, we do have it running up here, and you can get a better look at it. So basically what I'm going to do here is we're going to show the flows in between the attacker and the victim. So as you can see down there on the bottom left, there's our attacker, and we're going to set him as the source.
Click it.
Clicked. There we go. And set the victim as the destination. And we're going to show the flows in between them. And as you can see, there is a current flow that is built directing traffic between those two hosts. The HP SDN controller allows a lot of capability in illustrating the flows that are going between them. Most of you won't be able to see it, but that little tiny box in the link between the two switches is actually one of those packet counters, and it will show how many packets are matching that flow. So you can actually see the status of network traffic going across that link. So let's go down to our attacker. I think I'm having a range issue with this mic,
Okay.
so if you don't mind clicking up there. Attacker. Whoa,
Yep.
wrong direction.
Don't click anything.
I'm not. See, this is the fight I'm telling you about.
Oh, it's happening.
It's happening. So basically, our attacker is going to send an evil ping, and we'll demonstrate it here once we get it up. We have our snort triggering on pings, and the reason we did that is because pings have a really great graphical view. You can see pings getting dropped. You can see pings getting how long they're taking going. And so we're going to run this this attacker script and have him attack.
Oh yeah, this is happening. Aren't you glad it's not a live demo? It would be a lot worse.
This was planned. This is planned. It's a review, in case you missed something. Yeah, there will be a there will be a test.
We don't have prizes. You can just leave with your dignity.
Yes. We all missed Joan Jett.
Almost there. Don't click anything.
By the way, this is Prezi. It's a great presentation software for those of you that have not seen it before. Highly recommend it. It's like $35 for a year or something, and it makes your presentations really cool and not
There we go.
not PowerPoint.
That's
Okay,
the
so
attacker.
there's the
Video's
attacker.
already running. Sorry.
He's sending his evil pings, and as you can see, look at this third ping. Notice how it's taken a little while. There's your third ping. That third ping took 11 milliseconds. That is because that traffic was just redirected. This attacker still thinks he's hitting his victim. In reality, he is not. He's hitting a VM that we stood up inside our honeynet and doesn't realize it. And this is allowed. You can do Nmap scans, you can do anything, and they just continuously scan that host, him thinking that he's still in the same place, when in reality, there's been no change. He is actually just talking to one of our hosts that we are now fully monitoring. What happened here is our appliance triggered on this attack. As you can see, it connected to our snort logging server. It then detects an attack and builds and sends flows to the controller. So it detected our attack, builds all the flows, sends them all to the controller, and our attacker is fully redirected to the next host. So let's real quick look at what happened here. So the host, the honey host, has the same MAC address and same IP address as the original host did. And so the controller thinks there's two hosts that are coming out of two different switches. The controller's a little confused. But if we look at the source and destination, it's now no longer following that original path that we plotted. It's now going through the honey switch into the honey host. He is no longer talking to the same host. We have completely dynamically redirected this traffic to isolate that attacker fully, so he can't talk to anything else on the network except what we want him to within our honeynet. The implications of this are we can now, due to those attacks, we can now spawn VMs and spawn networks inside that honeynet, so he actually thinks he's pivoting within our network, when in reality, he's in a glass box that we're watching. Really incredible stuff. We are able to send, put up a Linux namespace, for example, listening on port 80. He now thinks he's talking to a web server. That sort of thing is really easily done with software-defined networking and redirecting that attacker.
So why does this matter to us? Well, like we said, we love SDN, and as we try to allude to you, SDN's here. It's already being used. It's being used heavily by large corporations, government entities, and it's been used for years and years. The thing is, as it moves closer and closer to our homes and the small to medium data centers that you guys might frequent, we need to be able to understand SDN. We need to be able to recognize the security implications, the threats that are inherent with it, and we need to find creative ways around that. We need to innovate. And the Open Networking Foundation, they've kind of been the lead for development of the OpenFlow protocol, development of the OpenFlow switch specifications, and they have a lot of buy-in from all these commercial vendors. But again, on the security community side of it, it really will require innovation and collaboration among us to build that framework. SDN can be a security instrument. That's the beauty of it. A traditional network moved packets. An SDN network can move packets smartly. So we can leverage the sensors that we already have, the appliances that we already have, all of these things that we already have. We can leverage these, interface them with simple programming, and we can create a more dynamic defense within our network. So right now, we love SDN because it is a network that can fight back.
So that's a broad overview of SDN and security. There's so many rabbit holes that this goes into, so many beautiful aspects depending on what you're good at. So if you're a coder, man, there's a lot of stuff to do. If you're a networking person, there's a lot of stuff to do. It requires a community effort, and that's all we're trying to show here. So at this time, that's all we have. We're running a little short on time. If you guys have any questions, we're happy to answer them. We do have the setup over here. I don't know if we're going to have time to pull it up all the way, but what are your questions?
Really?
Sweet.
Oh.
We explained it really well, or everybody's really confused.
You guys are like, yeah, we're going to go do SDN. It's that awesome.
Oh, we got a heckler.